Hello, my name is Nitin Karandikar. I'm the chair of pathology at University of Iowa. Today is August 5th, 2020, and believe it or not, just a few days ago, I finally joined Twitter, a very late entrant into that game, and I sent my first tweet. I've been on Facebook for several years, but entering Twitter was a whole different experience. From outside, I had a very different idea of Twitter, but now it's just amazing to see so many old friends and very inspiring to see so many people in the world of pathology, immunology, science, sharing their opinions and also partaking in a lot of educational activities. So I myself was inspired and decided to throw a pebble or two into this ocean. On the research end, I'm an immunologist, but on the clinical end, I'm a hematopathologist, particularly interested in diagnostic flow cytometry, diagnosing leukemias and lymphomas, which I think of as tumors of the immune system. And I decided, let's put some cases out there and then provide opinions and innuendos and interpretations of that. But then I realized before jumping into cases, I needed to just put online an introductory lecture, essentially, about flow cytometry, a talk that I've given at state, national conferences. I do it every year for incoming residents and externs and fellows over here. And I think it'll be great to just put it out there in case anybody wants to go and see it. Also, I realized that I cannot squeeze it into small snippets of 2 minutes, 20 seconds each, but I'll try to break it up into a little more digestible pieces, and you can forward through whatever you don't want to hear and stuff like that. So let's see how this all plays out. I'm going to share my PowerPoint here and then fairly quickly get started. So I'll talk about this hashtag go with the flow towards the end of it, maybe have a separate clip explaining why I'm using that term. For now, you can interpret it in any way you like. So in this first video chapter, we will just go through the introduction to the introduction of the very basics of flow cytometry. I also want to say this, the entire talk, all the video chapters together are very clinically focused, very diagnostically focused, and they're very practical aspects of flow cytometry, lab workflow analysis that I will go through, trying to cover what is done in many of the labs around the country or the world, and trying to leave some of the fancy stuff out of here that we use on the research end. So just to jump into it, this is the overall outline of all the videos put together. We'll go over some of the principles of flow cytometry. That will be this particular chapter. And then we will go into lab workflow, utility of flow in hematopathology, and by and large, I will focus on the diagnosis of hematolymphoid neoplasia, how flow is used, what are the principles, how do we approach the diagnosis of leukemias and lymphomas. And then we will get into cluster analysis and some real cases so that after that I can start putting whatever interesting cases we come across. So in general, the diagnostic approach to leukemia and lymphoma has changed over the years. A while back, maybe 10, 15 years ago, it was time to give up this oversimplified FAB classification that was used in the past, or the working formulation, which was purely based on how things looked under the microscope. And that gave rise to this WHO classification through a stage where it was called the real classification. And we realized that leukemias, lymphomas are biologic entities, and we needed to think of them in that way. And because of that, the diagnosis, classification, and management of hematolymphoid neoplasia became, by definition, a multimodality endeavor. It is not based on any gold standard of either morphology or genetics or immunohistochemistry or flow. All of it is required to make a good diagnosis. And the one thing that I would stress to all residents, fellows, is that the untreated status of the patient is a very important time point for a complete investigation. So if you get a lymph node in the gross room and there's a suspicion or even a whiff of a hint that this might be a lymphoma, save some tissue in that flow media. Maybe you don't need it later, or save some tissue in media that can be cultured for cytogenetics. Maybe you don't need it later, but saving specimens at that untreated point will be very good to get a complete diagnosis so that appropriate management can be initiated. And of course, most of the people seeing this video, I assume, are going to be from pathology, but it still bears stressing that good lab and pathology support is a critical component of the patient management team. So even more so, of course, we are right now in this COVIDian world, and we totally realize how important pathology and lab support is for patient management. So what do I mean by the multimodality approach? We have to use all information available, including the clinical presentation, history, the exam findings, imaging studies, if available. And of course, within pathology, we are responsible for the morphology. How does it look under the microscope? The immunophenotype, whether you do it by immunohistochemistry or flow cytometry. The genetics of a tumor, extremely important, particularly in some situations where they would be, or they would override anything else that you find. And then the importance of each of these is purely determined by the situation. So it's a situational gold standard. Not any one of these are the automatic gold standard. So going to flow cytometry, just some definitions. Obviously, as the word suggests, cytometry is the measurement of physical and or chemical characteristics of cells or other bioparticles. Flow cytometry is when these measurements are made while the cells pass single file through a measuring apparatus. An extension of flow cytometry is flow sorting, where you divert and collect cells with specific measured characteristics. By and large, when we use the term flow cytometry, really what we mean is fluorescence-based flow cytometry. Otherwise, if you think about it, even our standard CBC machines are excellent flow cytometers. Many of them are actually using at least one fluorescence-based parameter as well. But when you're doing multiple fluorescence-based parameters, that's when we tend to use the term flow cytometry. So what are the basic concepts of this technology? Well, it's a fluorescence-based tool. It's a very powerful, precise diagnostic tool. And it is based on the fact that cells express antigens. This is what immunologists would call them, or markers, as we call them in the context of pathology. And these markers can be used singly or in combination to identify the characteristics of those cells. For example, and I'll take this example through these bullet points, we know that B cells express CD19. So CD19 is a marker for B cells. So expression of these antigens is then determined by staining with the corresponding antibody. So in this case, if we want to detect B cells, we would stain cells with an anti-CD19 antibody. And the antibody, in this case, is conjugated to a fluorescent tag, which can then be detected by the instrument. So for example, this fluorescein isothiocyanate is a green tag that can be put on the anti-CD19 antibody and then used to stain the cells. So if the cell expresses the marker or the antigen, it will then fluoresce with the color of the tag. For example, a B cell stained with CD19 FACSC antibody will fluoresce green. And so the instrument will detect it as a green event or a green cell. And just to make a fine point of this, because the cell is detected as green, we are assuming that it got stained by the FACSC antibody, which we knew was anti-CD19. And so then we make the assumption that the antibody is attaching to the CD19 molecule and therefore concluding that this population of green cells is B cells. Sometimes antibodies can attach in different ways. Cells could be autofluorescent for green, and we'll get into that later on in the talk. And a combination of antibodies is typically used to identify and characterize normal as well as abnormal populations of cells. So for those of you who think visually, like I do, let's say this is a mix of peripheral blood cells, which within the lymphocyte population is going to contain T, B, NK cells. And we just use a two-color example here. Let's say we want to find what percentage of these are B cells and what percentage of these are T cells. You can take an antibody, CD19 here, which is a B cell marker stained or tagged with FACSC, which is a green fluorochrome. And let's say you take an anti-CD3 antibody, which targets T cells, tagged with the red fluorochrome, PE. Then you always use antibody in excess. So some is left over, you mix these, it'll, anti-CD3 will attach to all the CD3 containing cells, CD19 for B cells. The rest of the antibodies are washed away, and then these cells are run on a flow cytometer. The settings of a flow cytometer are set in such a way that negatively staining populations are also seen. We set it up so that these are not squished somewhere here. We want to see the whole population ideally. And then along the green channel of the flow cytometer, you realize that you're detecting this cluster population. And so you conclude these are B cells, you can quantify it. So let's say 2% of these cells in this particular patient were B cells, CD19 positive. And then along this red axis, you're seeing a 20% population that was staining red. So you conclude, yep, these are T cells. And then normal cells are not going to express 19 and 3 together. So you don't detect any cells that are double positive. So nothing from here is shifted here to indicate that it is 3 as well as 19 positive. So 0% there. So a very simple example of how this could work. So what is measured as these cells are passing through? Well, you can measure intrinsic versus extrinsic parameters. So intrinsic like cell size, cell granularity, extrinsic such as antigens or markers that we stain for using antibodies. You could do structural things again, like granularity, complexity, vacuoles, or functional parameters of cells, calcium flux, for example. This is not as much used for clinical diagnostics yet. As an example, when somebody talks about 12-parameter flow cytometry, we are typically measuring two intrinsic parameters, one of them called the forward light scatter, corresponding to the cell size, and another one called the orthogonal light scatter, which loosely corresponds to cell complexity or granularity, vacuoles, that sort of thing. It is scattering light. And then in addition to these two physical parameters, people are measuring 10 fluorescent markers in a 12-parameter flow cytometry. And these are usually 10 different markers or protein antigens that are stained by 10 different fluorescently tagged antibodies carrying 10 different fluorescent markers. Okay? So that's the idea of how parameters are measured. How does the chemistry accomplish itself? I'll use a simpler example of a 4-color or 6-parameter machine called the FACSCalibur. This particular machine has 2 lasers. It is still a workhorse in many clinical labs, this or even research labs. This argon laser emits light at 488 nanometers, monochromatic light. And it has another laser, the helium neon laser, which emits light around 635 nanometer wavelength, okay? So monochromatic light. If you remember how fluorescence works, fluorescent markers have an absorption spectrum. So they are going to absorb. So if you have light near the absorption spectrum, they're going to get activated. And as they come back down to rest, they're going to emit light, an emission spectrum in a different wavelength. So as you notice, these first 3 here, FACSC, PE, and PERCP, are fluorochromes that get activated near that 488 nanometer. So the argon laser is going to activate these 3 fluorochromes, and they are picked in such a way that the emission spectra are different or distinct from each other so that the machine can read them, read 3 different signals. And then in this machine, you accomplish a 4th color from APC dye because its absorption wavelength is closer to the helium neon laser. So it gets activated by the Heine laser light, and then it emits light in a 4th wavelength that can be detected. So again, for those who think better visually, imagine the room that you're sitting in is the entire flow cytometer. This flow cell is where a tube of stained cells is attached below it. And then let's say the cell is shooting right at you from the screen through this flow cell. As the cell is shooting at you, these 2 lasers are going to shine their light on that cell, on each cell that is passing through. That cell, the same argon light, is detected by the forward scatter detector, and that's sort of a shadow of the cell corresponding to the cell size. And the cell will be able to reflect light all over the place, scatter light, and one of those degrees, 90 degrees here, is taken in and detected by the side scatter laser. So this laser is detecting that 2nd physical parameter we talked about. And then depending on the dyes that were able to stain the cells based on its markers, it's going to get activated by the argon and or helium neon laser and emit light in those 4 different wavelengths we talked about. And so it passes through a whole system of mirrors and bandpass filters and so on, and gets detected by these 4 different detectors. And so you have 6 readings on each cell. Now, of course, modern flow cytometers that are constantly being tweaked. Some of them are using this trigon and octagon technology where to save energy from the light, it is taken in, passed through a bandpass filter on the first detector, but then this detector is also a mirror that is reflecting all light under 735 over here. Then that is passed through here for detection, the rest is reflected and keeps going. Really cool technology. And of course, there's even more and more invention going on. In our clinical lab, we use the BD FACSCanto, which is a 10-color, 12-parameter machine. On the research end, long time ago, we were able to get, of course, a BD LSR2. This has become a workhorse at many centers for immunology research in particular, doing about 16, 17 color maybe. Now we recently got a Cytec Aurora. These guys are proliferating everywhere as well. And this is capable of doing 30, 40 color. We haven't done our first 30, 40 color experiment yet, but we shall see if it's really able to do that. And so the standard question that used to be asked, not so much anymore, is why so many colors? And the simple answer is that the more parameters one can measure on a single cell, the higher the diagnostic accuracy, because tumors are not going to be 100% of the population, particularly when you're trying to detect minimal residual disease. The more information you have on that small population, the better. So for example, if we know the cell size and the cell granularity, we are already able to separate out different populations like granulocytes, lymphocytes, monocytes, for example. That's how our CBC machines work. So they don't need fluorescence to do that. But add to that, let's say now you stain for CD19, now you know that this particular population within the whole population, this subpopulation is that of B cells. If in the same tube you can now get kappa and lambda staining, you would say, okay, these B cells are splitting into kappa and lambda, so they look polytypic, they're normal. Or you would say, here's a big population of purely kappa staining cells, that must be a B cell tumor. Once you do that, then immediately you want to look at CD5 and CD10, ideally in that same tube. So now you know that, okay, this population seems to be CD5 positive, but CD10 negative. And in that case, if in that same tube, you could stain for CD23 and FMC7, maybe CD200, you might clinch the diagnosis of CLL, SLL, or mantle cell. So it is important to have that kind of capacity for a greater confidence and greater diagnostic accuracy. You can make do with fewer colors. 4 color can work, but more colors, 10, 8 color, just gives you more diagnostic accuracy. And before ending this first part of the talk, I have to just talk about this concept of isotypic controls, which sometimes can get confusing. So as I said earlier, cells can fluoresce on their own in some colors called autofluorescence. You don't want to read that as positive for a marker that we are detecting in that color. And so tends to be that larger cells like these blasts here or monocytes, they tend to have more autofluorescence. And some of these same cells also tend to have either FC receptors or the ability to bind antibodies, not from the end that is detecting the specific antigen, but let's say from the FC portion of the antibody, or just getting stuck non-specifically. And so the way to control for that, there are many different ways, there's fluorescence -1, etc. In clinical labs, a typical way to control for that, either people run an unstained tube, or they run tubes that were stained by isotypic antibodies. So like a mouse IgG1 or a mouse IgG2A, which is targeted to non-human molecules like KLH, keyhole lymphethymocyanin, or albumin, something like that, that shouldn't stain any human cells. And by and large, what happens is small cells like these lymphocytes here in this light blue color tend to behave themselves. So these cells would probably just be staining right here. And these larger cells like these blasts or these monocytes would be ones that inch up due to either autofluorescence or attaching non-specifically to these antibodies. And so you can use this cutoff. Now, I am particularly not fond of quadrants and linear cutoffs. So we look at clusters, look at shifts, and we'll get into that. But just as a concept, let's say to call these blasts CD34 positive, because both are FITC, you want these larger cells to stain beyond this cutoff. And as you can see, the only cells staining beyond this cutoff are these red cells. They are your true CD34 positive blasts. All the others, these blue cells, while they seem shifted off along the x-axis, these are not true CD34 positive, because even in the unstained or this isotypic control stained tube, they would have landed somewhere here, and you have to use that as the cutoff. Lymphocytes, as you can see, very well behaved right in that first decade of this old FACSCalibur type of dot plot. So that's the idea. When in doubt, look at your unstained, a fluorescence -1 or isotypic control tube. Isotypic controls are not necessary. You can use negative staining with some other antibody. Like if you know a population is CD3 negative, you can use that tube to use as an isotypic control or autofluorescence cutoff to measure some other antibody. But most labs, I think, are still running either an isotypic control or an unstained tube. So that's the concept. I think we are going to stop here for this first digestible area. I will end with this particular plot just based on forward and side scatter. You will see how these events lie at several places. It's always good to have an internal lymphocyte control. This is what we would call small cells in hematopathology. Somewhere here would be our medium cell processes, and somewhere here would be our large cell processes. One point I would make is that what we call large cells in HemPath are probably still small cells in SearchPath. For example, small cell cancer of the lung would be somewhere here, similar to a large cell lymphoma. These small cells in HemPath are the small blue dots that you just ignore under a SearchPath slide. So the only surprise here are these basophils. So just to go through these cells first, myeloblasts are larger cells. Monocytes are also larger. They have more complexity, so they're lifted off, as you can see, for their vacuoles, maybe weird-shaped nuclei. The promyelocyte is the largest neutrophil cell coming from here, and also very granular. And then as they get granules, they start shifting lower in size, as you see under the microscope, to become these mature granulocytes. Eosinophils tend to be smaller in size, low forward scatter, and very, very granular. So they're way up here. The basophils are always a surprise. Turns out their granular properties are such that they don't really have high orthogonal scatter. They don't reflect light, the refractive index, and the way they are packed. They tend to scatter right here. Healthy basophils will probably scatter somewhere here between lymphocytes and monocytes. These happen to be from a case of CML, so they're not perfectly in the normal position. But that's how populations scatter, just based on forward and side scatter. We will end there, and I will continue with part 2 of this talk in the next video chapter. All right, take care.